Why, hello there. It's Miss Heaton signing in to talk with you about chemical equilibrium. By now, you probably have done an experiment in class where you saw reactions that were getting to equilibrium, and we're going to talk about what's going on there, as well as some calculations. So you will want to have a calculator handy. First, let's talk about the concept of reversible reactions. In our last unit, we saw these energy diagrams where we said, well, you can either go from reactants to products, or you can go in reverse. You can go the opposite direction, from the products to the reactant side. Theoretically, any reaction can be made to go forward or made to go in reverse. You just got to have the right conditions. And here's an example of that. We've got ammonia being produced. Nitrogen and 3 hydrogens combine to make 2 ammonia molecules. However, the reverse can also occur. Those ammonia molecules can break down into nitrogen and hydrogen atoms. So any reversible reaction is one where the products also can react or break apart to reform the reactants. So here's what a picture might look like. At the beginning, we would maybe only put our reactants in, only nitrogen and hydrogen, and we would let time pass, and then by the end, what would be left in our container is not all of the nitrogen and hydrogen used up. I mean, look at this. We have enough nitrogen and hydrogen to do the reaction again. But those did not choose to react, or if they did, they formed ammonia and then broke apart again. So this is, this could be at equilibrium. It could just be like on its way to getting to equilibrium. If we took another picture a few minutes later and it looked the same as this picture here, we would know we're at equilibrium. Well, what exactly is equilibrium, you might be asking? Well, it's a balancing out. And you saw this in the tube lab. How do you think you saw this in the tube lab? Well, you got to equilibrium when the amount of water in each tube wasn't changing anymore, and that is exactly the definition of equilibrium. Equilibrium is just a state of balance where the rate of the forward reaction and the rate of the reverse reaction are the same. So graphically, let me point out, this is not the graph that you graphed in class. Over time, if you were to graph the rate of the reaction, how fast it's going, at the beginning, you would have a pretty fast reaction for forward reaction, very little going in reverse because there's none of the reverse products there at the beginning. A little bit later, their rates would start to even out, and eventually they're going to end up with the same rate. We saw this in the tube lab where the same amount of water was being transferred forward and backward each time eventually. Although at the beginning, the reactants were the only ones with water in it, so the rate or amount of water going forward was much more than the rate going backwards. Equilibrium is also where the concentration, that's what these brackets mean, concentration of products and reactants are constant. A lot of people get confused and think that at equilibrium you have to have equal amounts of products and reactants. That is not true. What has to be equal is the rate. What is different from each other is probably the products and reactants amounts. But those amounts are no longer changing. Like in the tube lab where we were transferring water still, the reaction was still happening, but no more water overall was being added to either side. And graphically, it could look one of two ways. You could either have the top scenario where they even out but don't ever cross, or you could have the bottom scenario where over time the concentrations start to level off like this, but initially because you had maybe more products, you had less products and you needed to end up with more products, the graphs cross. Both of these show equilibrium because the amounts of each reactant product, the concentration, is not changing at the end. So equilibrium is there at the end. I want to point out that equilibrium is dynamic. Just like in our experiment, we were still able to transfer water back and forth and still be at equilibrium. Same thing occurs in a chemical reaction. You do not stop once you get to equilibrium. The reactions keep happening. But again, you're going to see the rates being equal to each other for forward and reverse, and the concentrations of reactants not changing and the concentration of products not changing. This link right here is a great animation. You can mess around with it a little bit. I'll pull it up here for you. You can change the number of molecules. You can change the temperature. Just turn the plot on and you will see a graph. For example, at this low temperature starting with more A, over time you see the reaction is still happening. There's still red things turning blue and blue things turning red. But they do start to kind of even out, although there will be temporary bumps. Over time they will kind of reach a plateau or a flat line. Okay, let's quantify it. This is where your calculator is going to come in handy. equilibrium constants are a way to quantify where equilibrium is, and we'll use the symbol KEQ. Please note that this is a different K than the rate law constant that we used in our last unit. I don't know why they picked the same letter, but this is an uppercase K. It's basically going to be the ratio of products and reactants that should be there at equilibrium. And once we know K, we know when equilibrium will occur. And it will be the same for a reaction unless you change the temperature. And we saw this in our experiment as well. Changing the temperature or the size of the tube changed the rates of the reactions, and it threw off when equilibrium is going to occur. So the general idea is that you want to do products divided by reactants. And a couple things to note, the coefficients are going to tell you what the exponents are going to be. Again, this is different than the rate law stuff that we were doing before. And solids and pure liquids don't get included because they don't have concentrations. If it's a pure solid, it's like 100% concentrated. And if it's a pure liquid, it's 100% concentrated. So it doesn't have a concentration. So in our example here, we have 2A reacting with B to make C and 3D. By the way, this is one way to draw those double arrows that I showed at the very beginning. The double arrows mean you can either go forward or backward. So here we're going to do products divided by reactants. The products are carbon, or C. Oh wait, that's a solid. It doesn't get included. But we do want to put the D there. And the coefficient here is not going to be multiplied by the concentration, but instead that will become our exponent. That means it's triply important for the equilibrium. And then for our reactants, we have A, which is aqueous, and that will be to the second. And here's where a lot of people get confused. You are not adding B, you are now multiplying it in your denominator. And this whole quantity will need to be put in parentheses when you put that into your calculator. Now notice that we have the ratio between the products and the reactants. If you end up with a ratio that's bigger than 1, that means you've got more on top. That means you've got more of your products at equilibrium. If your K value, when you calculate it, turns out to be less than 1, that means you've got a bigger number in your denominator, so you've got more of the reactants at equilibrium. So let's do a little calculation with that. Consider the same reaction. This is example 2. Same reaction as an A, so this is our formula for KEQ. We want to calculate the value when these are our concentrations. So what you'll say is KEQ equals D to the third. D is 9, so D cubed, times the quantity A, which is 3 squared, times B, which is 2. Notice that I deceptively gave you a concentration of C, which is invalid because C is a solid and can't really have a concentration. So then you plug that into your calculator. 9 to the third divided by the quantity 3 squared, which is 9 times 2. And I believe that turns out to be 40.5. Since that number is bigger than 1, that means that we've got a bigger number on top, so our products are favored at equilibrium. That means you'd end up with more quote-unquote water in your tube, or more products, more of that substance at equilibrium. Now, you're not always at equilibrium, and that's where our next factor comes in. The reaction quotient we call Q because it is a quotient. That means like divided by. Basically, it's just the same thing as KEQ, but when you're not at equilibrium at any given time. It could also include equilibrium, but typically you're either like at the very beginning or very like middle of a reaction. So again, it's going to be the products divided by the reactants. And what you can do is calculate Q given your given numbers and compare it to the K value. And based on that, you can figure out what has to happen to get to equilibrium, because that's the goal. Everybody wants to get to that happy equilibrium balance in their life or reaction. So let's think about this. If when you do your ratio of products to reactants, maybe I'm going to make up a little reaction here. We got reactants going to products, but it's a reversible reaction, so it can go either way. The value for Q is going to be the products divided by the reactants, and I'm just going to abbreviate them a little bit more. And the K value will again be products over reactants, but at equilibrium. So let's say that you get a Q value that's too big. That would happen if you had like a huge amount of products. So we got a whole bunch of products. That's really big. And when you divide a big number divided by a smaller number, let's make this reactance amount smaller, you're going to end up with a number that is too big. Your Q value is going to be bigger than K, and so the reaction is going to freak out and say, oh my gosh, we got too much products, let's get rid of them. So which way will the reaction shift? Well, you're going to need to go in reverse to get rid of some of your products and make more reactants. So that means it's going to shift in reverse if you have a Q value that's bigger than your K value. Obviously, if your Q and your K value are equal, well, duh, you're at equilibrium. Because the ratio of products and reactants would be the same as it should have been at equilibrium. Let's do one last scenario. If you have a small amount of products and a huge amount of reactants, when you divide those, you're going to end up with a smaller number than you should have gotten at equilibrium. That means you have too much reactants, and so you need to get rid of them. The reaction's going to freak out until it goes forward a whole bunch, makes more products, get rid of some of those reactants, and now you're going to be at equilibrium. So if Q is less than K, you need to shift forward. You need to shift to the forward reaction, favor the forward reaction. Great. Let's try an example of that. We've got this fancy chemical equation here with actual real chemicals in it. Imagine that. Notice that you've got a solid here. So let's calculate K for this reaction. K is going to be products over reactants. So our first product is Na2SO4. And we're going to divide that by our reactants, NaCl. And it's got a coefficient of 2, so that's squared, times BaSO4. Again, notice that we excluded the BaCl2 because it is a solid. So let's plug in our numbers here. We see that the Na2SO4, the sodium sulfate, has a concentration at equilibrium of 3. NaCl has a concentration of 5, but that's squared because of its coefficient. And BaSO4 is 2.3. So plug a chug in your calculator, and I believe you get 0.052. It's a pretty small number. That means you've got a bigger number on bottom, a bigger amount of reactants, and a smaller amount of products at equilibrium. So this one favors the reactants because K is less than the value of 1. You know, if you had equal amounts of products and reactants, that would divide to make 1. Great. One last part to this. Let's throw Q in there. Let's say I've got a random container with this reaction stuff in it at the same temperature. Let's find what the Q value is based on this scenario and figure out which way the reaction has to shift to get back to equilibrium, back to this 0.052 ratio. So Q is again going to be the same equation as K, but now we just have random numbers. The sodium sulfate concentration is 9. The sodium chloride concentration is 2, so that's squared. We'll multiply that by the barium sulfate concentration, which is 1.5. Notice that we're again excluding the barium chloride because it is a solid. When you plug or chug that in your calculator, double check me, but I think you get 1.5. So let's compare our Q and our K values. If the Q value is 1.5 and the K value is 0.052, that means Q is too big. If Q is too big, that means, oh no, we've got too big a number on top and not enough number on bottom. So we've got too much of our products because they're on top. So if you got too much products, you need to shift away from the products, so you need to shift in reverse. Got that? So let's put this all together. Why don't you try this problem on your own? So hit the pause button and then tune back in and check your answer and see if you did it right. Okay, I'm going to go through this real quick. K is going to be products, P2O5 squared, divided by reactants, so that's P to the 4th times O2 to the 5th. Plug and chug your numbers in. These are going to end up being crazy numbers. These are really small concentrations, but when you end up plugging them in and dividing them out, you end up, because of all those crazy exponents, getting a number like 2.24 times 10 to the 15th for your K value. That is a really large number. What do you think is favored? Is it more towards the products or reactants? Well, since this number is, if k is bigger than 1, and this one's way bigger than 1, that means you've got a whole bunch of products. And then finally, to find the value of q, it's going to be the same process. Q is p205 squared, so that's 15 squared, divided by p to the fourth, so 15 to the fourth, times 15. Hey, they're all the same. Does that mean we're at equilibrium? Not necessarily. You don't necessarily have to have equal amounts at equilibrium. Remember, it's just the rates that are equal. Bringing it full circle. And then let's find our q value. When you plug that in, you get 5.9 times 10 to the negative 9th as your q, your quotient at this given time. So let's compare that to our k value. It looks like q is a really tiny number, so q is much smaller than your k value. That means, oh no, we've got too much of the stuff on the bottom. We've got too many reactants, so we need to shift away from the reactants, so we need to shift forward. Okay, if you did that right, I think you got the hang of this. Come to class, we'll continue to discuss it. If you made a mistake somewhere, if you don't understand something, write your question down and ask your teacher tomorrow. This is Miss Eaton, signing out.